Hey, good morning. Today we're going to work through a few problems on finding volumes on work, average value of a function, and integration by parts. So compute the volume of the solid obtained by rotating R about the x-axis, where R is this region. So we have, I'll try to stick to a similar color scheme as above. Y equals x squared. We have y equals 3 up at the top here. So I note that this x coordinate of this point of intersection is going to be a √3. And x equals 0, the y-axis, giving us this region. And it's being rotated about the x-axis. So we always want to be careful about which axis we're rotating around. If we were to rotate the same region about the y-axis instead, we'd get a very different looking solid, and of course a different volume as a result. Rotating about the x-axis. So I have my line at 3, which rotates around to a line at -3. I have my curve going from the origin up to √3, 3, and mirrored on the bottom here. I know that my x coordinates are going to go from 0 up to √3. So we might do this by shells. We might do it by the disk method. Let's go with the disk method since we did the last problem with the shell method. So we need a plane. So we're going to have this plane perpendicular to the x-axis. And this plane is going to have two circular intersections. It's going to have a circular intersection with the outer shell, so to speak, of this solid, the one that's from the line at y equals 3 being wrapped around. So maybe I'll draw that one in blue to try to keep our color scheme consistent. So this is the one with radius 3. And then we have an inner an inner circular section here that's related to this red curve being rotated around. And what's its radius going to be? Its radius is going to be, well, its radius is going to be this distance here, right? It's just going to be y or x squared. So what's my cross-sectional area A of x? The cross-sectional area is going to be the area of this annulus, this donut here, which is going to be the area inside the outer circle, subtract the area inside the inner circle, or that's just pi times the difference in the square radii. 3 squared minus x squared, or that's pi times 9 minus x squared. That's my cross-sectional area. And remember, with the disk or washer method, this one looks more like a washer than a disk. Our volume is the integral. We start adding these washers starting on the left at x equals 0. We continue adding washers until x equals √3. And we just integrate the cross-sectional area pi times 9 minus x squared dx. Again, a fairly straightforward integral to carry out, and I get 9 root 3 times 4/5 pi. A bunch of fractions and some annoying work with exponents and so on, but that's it we end up with. Okay, so moving on to a couple of interesting problems on work. So we did a fairly straightforward problem in work about just having a rope hanging over the edge of a building and then pulling that rope to the top of the building and seeing how much work was done. We remember that work is the integral of force, or if the force function is constant, it's just the force times distance. And we remember that the key was to think of the rope as a whole bunch of little small segments of rope over which essentially the force and the distance that we have to move that segment is constant. So we can just say that segment weighs a certain amount and it needs to be moved a certain distance. We can add all those up. We can take a limit, make it an integral, and so on. So that was how we approached this before. So what's different here? We have a 30-foot chain. We have a building 30 feet tall. So I have my building 30 feet tall. I have my chain hanging over the side of the building. It goes down just to the ground. So 30-foot chain. But the interesting thing here is that in addition to the chain, I have a weight at the bottom. A 50-pound weight. Oh, not 50 foot, 50-pound weight at the bottom. So, if you're thinking of maybe you have a packet of shingles attached to a rope and you're standing on a roof and you want to pull them up to the roof, how much work will you have done when you've pulled the shingles up to the roof? Well, the shingles have to get up there, but also the chain that's attached to them has to get up there. Well, and this should say chain instead of rope. This might seem somewhat complex at first, and we could set up an integral to directly solve this thing under a single integral. But personally, I like to just break the problem into a couple of different components. I think it's much easier to do. So I envision this as, on one hand, I've got to get the rope up to the roof. And on the other hand, I've got to get the weight up to the roof. So if I were to hypothetically just levitate this weight up on the roof, well, what do I have? I have a force of 50 pounds that just has to move this distance of 30 feet. Well, that's going to be an easy problem to solve, right? Instead of adding the complexity inside the integral, which was already, a complex thing, it's calculus. Well, split the problem into a couple different parts. And this is just a question of arithmetic. So what is our work done? Well, we're going to have an integral for the rope. We'll think about that in a second here. Plus, which is force times distance, 50 times 30. Okay, so this rope here, remember what we did is we took some segment, length delta x. So it has total weight, in this case, 2 delta x pounds. So delta x is in feet, so 2 delta x pounds. And we said that has to move some distance up to the roof. And if delta x is fairly small, well, the top and bottom of the chain basically have to move the same distance. So that has to move a distance, which we'll call x, where x could range from, if we take a chunk at the very top of the rope, near 0, to at the very bottom of the rope. This piece at the bottom of the rope has to move this entire 30 feet. And then each one of these little components, each one of these little contributions to the work is force 2 delta x times distance x, or 2x dx whenever we take the limit. Okay, so this is going to be x squared from 0 to 30 plus 1500. And that's going to be 900 plus 1500, or 2400 foot-pounds. So that's a little work in getting the weight plus the chain up to the top of the roof. Again, you probably could, or well, you definitely could set this up under a single integral and do it that way. But I think it's just so much easier to break it into two problems like this. I think it makes it easier to see where everything comes from. Now let's look at a similar problem that at first glance might seem much more complicated. And this problem involves, we have a 100-foot chain hanging off a building 70 feet tall. So what's the interesting bit here? So we have a 70-foot building, but a 100-foot chain, which means that 70 feet of the chain is hanging, but then 30 feet is just kind of coiled up here on the ground. So this might seem very complex because for a while, if you think of if you thought of the chain up here, even without the weight, it might make it easier to conceptualize. Each pull that I make on the chain, I get some more of the chain onto the roof. So what's left hanging off the roof weighs a little bit less. So the next pull is a little easier. And I can kind of see that the force that is being fought against at each pull was getting less and less as I get more chain on the roof. This one, though, I note that for a while, for the first 30 feet, every foot of chain that I pull onto the roof, I just pull another foot of chain off of the ground. So it's like a constant force for that, or a constant force pulling against me for that first 30 feet. But then after that, it starts to get easier. Again, I might try to wrap this under a single integral, but I actually think that it's easier to just, again, break it into two problems. So another way to think about this is, well, all of this chain has to get to the top of the roof. It doesn't much matter that whether I'm pulling on it or whether the chain is all, attached to itself, or, whether this is like, say, a bucket down here holding this chain, or whether that chain is free to unravel as I start pulling on it. Does that matter all that much in terms of the work that's done, in terms of the energy that has to be expended to get this entire mass at these different heights up to the top of the roof? Well, I don't think it does, right? So again, we can break this into just two problems. We could imagine kind of chopping the rope right here, and we have our 70 feet of rope that has to make it up to the top of the building, plus we have our coiled up 30 feet of rope down here that we can just kind of imagine as almost like being in a bucket, in a weightless bucket, that needs to make it to the top as well. So we can see that this is really the same problem as above. We have a weight that needs to move a constant distance, and then we have a weight in some sense that needs to move, certain parts of it need to move a further distance than other parts. So what's the work that's done? We still have 2 pounds per foot. Integral 0 to 70, 2x dx, just like up here, just getting that chain itself up to the top. Plus, well, here we just have a force that needs to move a distance of 70 feet. So what is the force? What is the weight of this chain sitting on the ground? Well, that's 30 feet of chain at 2 pounds per foot. So that is 60 pounds that has to move 70 feet. So this contribution to work is force times distance, 60 times 70. Or this is going to give me x squared from 0 to 70, or 4,900, plus 4,200. And that's what, 9,100 foot-pounds. Okay, so switching gears a little bit now. So moving on to the average value of a function, we did an example of this last time. We didn't talk too much about it. It's kind of a side topic, so we're not going to cover it in, tons of examples in it, but we will do this one example because this also, we'll see, kind of ties back to the idea of volumes. Okay, so we have an example here, the velocity of blood in a vessel with radius big R, length L, at a distance little r from the central axis is given by V of R equals P over 4 eta L, big R squared minus little r squared. P is the pressure drop, eta is the velocity, or the viscosity, length is L, radius of the vessel is big R. Okay, so what do we have? This P over 4 eta L, it's just some constant. So that's not going to play too big of a role. It's just going to kind of come along for the ride. But really what we have here is we have a region like this representing blood flow. So if we think of our vessel as kind of being roughly cylindrical in shape, we have flow like this. And this kind of makes sense. If you look at a riverbed, anything like that, the faster flow is going to be in the middle. Around the outsides, you have all kinds of boundary conditions, all kinds of interactions where cells are kind of rubbing up against the edges of the vessel, and the edges of the vessel are fixed. So there's some friction there, there's some interference, but near the middle, those liquid molecules are just surrounded by other liquid molecules. They can move much more easily. Okay, so if I just think of this as a function, f of r, so here's little r, and there's v. I note that if I find the average value of the function, I'm just looking for the average height. I don't have to go from negative big R to plus big R. I see the nice symmetry that I can make use of. I only have to go from 0 to big R. So I need to calculate this area here, calculate the integral, and then divide by this distance here, big R, to get F average. Or to get, I suppose, V average here. So the integral that we'll do goes from little r equals 0 up to little r equals big R. We have our constant P over 4 eta L times our big R squared minus little r squared d little r. And from A to B is 0 to big R. So what is B minus A? That is big R. So this is our V average. And this turns out to be, again, with a little bit of fairly straightforward integral. This turns out to be that constant P over 4 eta L times big R squared times 2/3. Now, something that might be interesting for us to know is, what is V max? So V max might be something that we could measure fairly easily with, an echocardiogram, something like that, or a Doppler scan, or we might be able to measure V max. So what is V max? Well, pretty clearly, that's V of 0. we shouldn't have any trouble at all proving that with basic Calc 1 techniques. And what's V of 0? T over 4a to L r squared. So this is 2/3 V max that we get for V average. Now we've answered the question, right? We certainly have calculated V average using our definition of average value of a function. So as far as the basic ideas in 6.5 are concerned, we're good, we're done. But we might want to go a step further and say, well, here I have an application, right? There's a reason that I want to find V average, and probably what I want to know is something like, if I have a Doppler scan, if I find V max in a blood vessel, how much blood is making it through that vessel per unit of time? My estimate then might be something like 2/3 of V max. But is that a good estimate though? Is this the proper way to approach this problem? So if we take it a step further and we say, okay, in this application, does this model match the thing that I'm trying to model very well? It doesn't seem like a terrible model, but I think we could do better. And we could do better if we recognize that, well, really, a blood vessel is not a two-dimensional structure. Rather, it's a three-dimensional structure. So I have this. I have a blood vessel that's like this, circular cross-section down here, and it kind of extends up like that. And the solid curve here, this kind of dome, represents my velocity at each xy point, at each two-dimensional coordinate. That might actually be what I'm interested in. So I might be interested in something like the volume divided by this cross-sectional area, rather than something like area divided by length. I might want volume over area. And how would that change? Well, the volume, nicely enough, is just a solid of rotation. It's just taking this region and rotating it about the vertical axis. So what can I do here? I can say that my volume is going to be the integral. And we might as well use shells for this. So we're going to be adding shells from r equals 0 out to big R. My shells formula, my basic shells formula is 2 pi radius, which is just r, times f of r dr. And again, fairly straightforward integral to do. If we do this integral, we get a volume of pi over 2 p over 4a to L. That's it, 4 there. Big R to the 4th. I don't know why OneNote loves to try to autocorrect my 4s to 9s. Okay, so r to the 4th power. This is sometimes called the flux, like the amount of material passing through a cross-sectional area, per unit time. So if this is the flux, I note that the flux is proportional to the 4th power. And there's some, I think it's something like Poiseuille's law or something like that, some very French sounding name that that says this, and this is really where this derives from. And if we want to find something that's a little bit more kind of meaningful, in the sense of an average velocity, we're averaging, recognizing that, you know, the blood flow the blood that's moving fast is near the middle, but there's not a lot of that. The blood that's moving slow is near the edge, but right, that annulus has a much larger area. There's a lot more blood near the edge of the vessel than there is in the very middle of the vessel. There's a lot more that's moving slowly than that's moving fast. So what's my average velocity? It might be better to, again, take this flux, divide by the cross-sectional area. No matter what I try, if that's too close together, it just connects it. So this is my flux times 1 over. And then the area of this circle on the bottom here is going to be what's in a circle of radius big R. So it's pi big R squared. So I see my pi's go away. I see my R to the 4th becomes an R squared. And I have 1/2 P over 4 beta L R squared. Now note that even in the 3-dimensional version, V max is still the same. Right at 0, 0, that's of the velocity at that point, that's still V max. And I note that I get my average velocity now looks more like 1/2 of V max, not 2/3 of V max. So while 2/3 of V max would be the correct answer from a naive standpoint, if we think about it a little more, we might not want to use that model. We might prefer, say, a model more like this. Okay, and then the last topic for today, integration by parts. So we did a problem or two in class of integration by parts, and you know, a couple of notes. Oh, my sometimes Outlook does, or OneNote does not cooperate with the equation editor. So sometimes when I type integral of log of stuff, it puts the log in front of the integral. I have no idea why. I'll just blame it on Microsoft, like I blame most things on. But yeah, so we did integration by parts, and we saw that the idea was that if I have the integral of the product of two things, u times dv, I can do some work and swap them into the integral of v du. What does that let me do? Well, dv becomes v, so I have a piece that needs to be integrated, and u becomes du, so I have a piece that can be differentiated. Why is this a useful technique? Well, certain function types, particularly these first three, get simpler when we differentiate them. A log, inverse trig functions, and algebraic functions like power functions, when we differentiate them, they tend to get simpler. So if I could pick something like that to be u, maybe when I differentiate it, du looks a lot simpler. And then provided that I can integrate what's left, maybe this integral on the right-hand side will be easier to do than the one on the left-hand side. Okay, so let's take a look then at integral of log of 3x dx. Now you might have trouble getting started here. You might say, well, but I need a u times dv. I only see one factor here. Right, this wasn't like an, you know, x e to the x kind of deal where you say, okay, integral x e to the x dx. Well, I see that there's two factors there. Well, we actually do have two factors here. We actually have log of 3x times dx. We could certainly pick dv just to be dx. There's nothing wrong with that. So if I set u equal log of 3x. dv is dx. I note that I've accounted for everything in the integral. I haven't made up anything that's not in the integral. du is 1 over x dx, right? 1 over 3x, chain rule pops out of 3, the 3's go away. And v equals x. So the integral of u dv becomes uv x log 3x minus integral v du. And nicely enough, v du, x over x goes away. We just have integral dx, right? So much simpler integral to do. This gives me x log 3x minus x and then plus c. So with these log integrals, sometimes you just have to use the dx as the dv, and that ends up making things work out nicely because the log tends to put a power of x in the bottom. Okay, what about a definite integral? Well, a definite integral works in much the same way. So we'll look at this example. Zoom in a little bit. We'll look at this example. Integral from 4 to 9, log of y over root y dy. And like I kind of mentioned down here, what's the typical strategy for choosing what to pick for u, choosing what we would rather differentiate than integrate? And we see logarithm right at the top of the list. Let's see if that works. Okay, so if I pick, get my notes combobulated over here. If I pick log of y to be the thing I differentiate, then what does that leave? That leaves a 1 over root y dy for dv. Or that's a y to the minus 1/2 dy, and that's what dv is. du is 1 over y dy, and v, well, I add 1 to the power, so that's y to the 1/2. And then I divide by 1/2, so I multiply by 2. And what does this give me? This gives me uv 2 root y log y. And I just evaluate that from a to b. So that's from y equals 4 to 9 minus integral 4 to 9 v du. So 2 root y over y, that's 2 over root y dy. And this kind of thing happens a lot in integration by parts, where things kind of, where you kind of did an integral here, and then you kind of end up with a similar integral that you have to do for the second piece of integration by parts. So you see that kind of structure pop up from time to time. Okay, so let's do this evaluation. So 2 root 9, so 2 times 3 is 6, log 9 minus root 4 is 2, so 2 times 2 is 4, so 4 log 4. Subtract the integral, so this is y to the minus 1/2. So when I integrate it, it's going to be y to the plus 1/2. And then divided by 1/2 or times 2, there's already a 2 there, so I get a 4 root y from 4 to 9. I note that log of 9 is log of 3 squared. The 2 can come out, so that's 12 log 3 minus 8 log 2, same deal here, minus. So when I plug in 9, I get 4 times 3 is 12, minus a negative is plus. When I plug in 4, I get 8. So this ends up being 12 log 3 minus 8 log 2, and then minus 4. Okay. And last but not least, a classic example of integration by parts. So let's work through this one. These types of solutions come up in damped oscillations. So if you have, say, a pendulum or a spring or something that is acting in the presence of, say, air resistance, its deviation from equilibrium might look like that. It might be modeled by a function like this. So here, again, we look at this, really no idea how to do this in a simpler way. As an aside, we should always look and see, is there a simpler way to do this that, maybe in some cases I could get away without using integration by parts if I just know the antiderivative, say, or maybe I could do a substitution or something. So we should always keep in the back of our mind that we have other techniques and maybe choose the easiest or more straightforward technique over a more complex one. But none of these problems had that available to us. Now I have to pick something to be U and something to be dV. So the question that I usually ask myself is, what would I rather integrate? That's the thing I want to pick for dV. I have a couple different choices here. I could choose an exponential or a cosine. I think I'd rather integrate the exponential. I think I'm less likely to make a mistake there than integrating a trig function. Du then is going to be cos differentiates to minus sine, and we get a 2 popping out. Sine of 2 theta. And then V is just going to be negative e to the negative theta. And I need a d theta here. So this is going to equal uv minus integral v du. So what's v du? That's the minuses go away. I get a 2. I get an e to the minus theta. And I get a sine of 2 theta d theta. So I always have to make sure to keep all of the accounting, all the bookkeeping right, and I think everything looks right. Let's make this a plus -2, just to keep track of that negative. Sometimes that can be a problem in integration by parts, is forgetting about that negative in front of the integral sign. But something that I noticed is that I got back a very similar integral to what I started with. So in some sense, it seems like I didn't really make it anywhere. I didn't make any progress. We might realize that if we do this a second time, if I do an integration by parts again, the sine is going to integrate to a cosine. And I'm going to get back, in fact, something that looks almost exactly like what I started with. Well, if I do that, I might be able to take the thing that I started with, call it I for integral, some function of theta. And I might be able to set I equals stuff plus I, and then solve for I. So let's try to do that. So what do I want to pick to be U here? What do I want to differentiate? Let's differentiate this guy. Let's differentiate this guy. Let's integrate this guy. So dV is -2 e to the minus theta d theta. And then U is going to be sine 2 theta. And I think I've accounted for everything. Du, sine differentiates the cosine. I get 2 cos of 2 theta d theta. And V is going to be 2 e to the minus theta. I still have this bit to bring down. You see why I put the negative sign in there now, because I don't want to have to remember to distribute that negative throughout. That would be a very easy place to make a mistake. And then I need plus uv, 2 e to the minus theta, sine of 2 theta, minus integral v du. So minus for e to the minus theta cos of 2 theta d theta. And I now see that I have exactly the integral that I started with. If I call this something like I note that I have, and let's call this maybe f of theta. I note that I have I equals f of theta minus 4I, which says, well, 5I equals f of theta, I equals 1/5 f of theta. Or this tells me that my integral is negative 1/5 e to the minus theta cos of 2 theta plus 2/5 e to the minus theta sine 2 theta, and then plus c. Yeah, not the nicest looking integral. We could certainly factor out an e to the minus theta and get a combination of a cosine and sine of the same frequency. We could wrap that under a single trig function with a phase. So we could massage this a little bit, make it look a little nicer. But that is the answer, and that's where we'll leave it for now. Okay, so that wraps up our supplemental material for these first couple weeks.